Thanks, John. My name is Mark Negro, and today's webinar is a shortened version of a 1-hour lunch and learn type presentation Lord typically does in person at our customer's facility. This specific version will be focused on the electrification of aircraft. Today we're going to cover the scope of our discussion with passive elastomeric isolators, an introduction to vibration and transmissibility curve, considerations when you're selecting an isolator. We'll briefly discuss Lord's product offerings and talk about some mounting strategies when using isolators. We'll talk about Lord capabilities and finally some characteristics that affect the performance of isolators and elastomers. Lord provides adhesives and coatings as well as motion control products to many markets and utilizes different technologies that are shown on the table. For this webinar, we'll be focusing on aerospace and defense type platforms, our elastomeric isolators, and these categories of technologies and topics. Though there are great technological advances in systems to electrify aircraft, the technical approach to utilize elastomeric isolators is not new. Using cell phones as an analogy, isolators are not smartphones. They're much more closer to what we would think of as flip phones. Now, why I say this? Lord has new developments with isolators and elastomer materials. However, they're never going to be digital and they'll never require power. The function of isolators are simply to allow the separation of vibration from one location to another. The value that elastomeric mounts provides enables other technologies associated with the electrification of aircraft. For example, protecting critical equipment, improving reliability of electronics and computer systems, reducing noise, and increasing passenger comfort and experience if people are on board. We are seeing the electrification of vehicles is occurring across different platform types. Lord isolators have been used across all of these platforms and are capable of meeting the requirements associated with each of these unique environments. One big question is, how should we approach isolators for electric systems or platforms compared to conventional systems? Before answering that, I have to share, I found an image Duracell released of an electric aircraft they're working to develop. Okay, so I'm joking about this, but reflecting on that idea at a 1,000-foot view is applicable to the question. There's many different configurations being pursued to meet goals and maximize performance by electrification. The source of vibration or things at risk of being damaged could be the same or different. However, the approach of utilizing elastomeric isolators is the same. If any of you recognize the person in this image, Isaac Newton. He hasn't changed, and the equations that he's written haven't changed either. That being said, understanding the characteristics of equipment that isolators provide value to is important. Here are some examples of what we say things that shake, or things that cause vibration that could cause damage to other things. We have electric power units, environmental control systems, pumps and gearboxes, or blades themselves. All these things spin and induce vibration because nobody can balance things perfectly. On the converse side, other equipment that isolators provide value to are things that are fragile or that could break. Some examples of that are guidance and control systems, our computer systems, valves, electronics, sensors and cameras, batteries, and then interior cabins for comfort when people are inside. Reducing the vibration transfer also reduces noise and improves the comfort inside a cabin. We're going to take a quick pause here and have a poll question. Have you utilized elastomeric isolators for mounting equipment in the past? All right, now we're going to continue to talking about some vibration theory. And don't worry, we're not going to get too far in the weeds here. First, to start off, recognizing we're looking at systems as complete units. On the left-hand side, the diagram of a suspended mass supported by a spring and damper system, the K and C that we know from our equation of motion. S is the structure where the vibration is coming in, or conversely, if we have something vibrating, the vibration is coming from the mass. The elastomeric mount provides a stiffness, K, as well as a damping, C, as part of the material characteristics. These two properties, stiffness and damping, can be demonstrated using different elastomeric-shaped golf balls. Using the same force on two different elastomers, the difference in stiffness can be seen. The stiffness is proportional to the elastic modulus of the elastomer. Damping can be demonstrated by dropping the golf balls from the same height. The difference between the height it was dropped and the height where it returns is the amount of energy that gets dissipated due to the material's damping. The amount of damping a material has and its elastic modulus are independent from each other. Two materials can be different stiffness with the same damping, vice versa, or any combination in between them. Besides for our BTR and BTR2 silicones, which most Lord catalog isolators are made in, Lord has a vast array of other elastomers that can be used to provide specific performance characteristics for your system. So here is looking at a dynamic system with looking at the transmissibility curve. We have two examples here, System 1 and System 2.
On the left-hand side, we have a transmissibility curve. On the x-axis, we have frequency. On the y-axis, we have transmissibility, which again is output divided by input. We're going to represent that curve using my hand and this mass. My hand is going to represent the input, the mass is going to be the output, and the rubber band is going to represent an isolator. Starting from the left-hand side at very low frequencies, as I create an input, we see that it's approximately the same as the output. When we divide the output by input, transmissibility, we get approximately 1. As we move right on the curve and increase in frequency, what we see is very small inputs produce very large outputs. When we divide the output by the input, we get a number greater than 1, which is the natural frequency or resonance of a system. When we continue moving right, increasing frequency, what we see is we can have very large inputs that produce very small outputs. This is what we call isolation, and this is the value that isolators provide to a system.
On the right-hand side, we have a graph of a transmissibility curve. On the x-axis, we have frequency. On the y-axis, we have transmissibility. Transmissibility curve has a natural frequency of 10 Hz, and the maximum transmissibility at resonance is 12. The other characteristic of interest is the relationship between the natural frequency and the frequency at which it transitions into isolation, which is typically a factor of square root of 2 times the natural frequency. The way we would read this graph is if we had an excitation at 35 Hz, we would read up from 35 Hz to the curve and over. What we find is we have a transmissibility of 0.1, where 10% of the vibration is transferring through into the mounted system, or we're isolating 90% of it. We can modify the natural frequency of a system by changing the stiffness. The equation on the top left is a general equation that describes that. We see the two factors affecting the natural frequency is Kt, the stiffness of the isolator, and W, which is the weight of the unit. Similarly, we can change the maximum transmissibility at resonance. This is a material property. What we also notice here that's important is as we reduce the amplitude at resonance, we also reduce the rate at which we go into isolation. So we have less isolation at high frequency, but less transmissibility at the resonance of the system. This is a trade-off that we have using elastomer. Now, how do we apply that to a system? We're going to use this graph here, and we're going to start with the red curve. That's intended to represent an input from an industry standard requirement for a vibratory condition. It starts at low frequency, low amplitude, and increases in amplitude into higher frequencies. If we have a box which has a fragility limit or a maximum capability of 10 Gs, and this input goes to 20 Gs at high frequency, we have a problem. If we were to mount this system on isolators, represented by the transmissibility curve in blue, we induce rigid body motion at low frequencies and we isolate the high frequencies. Again, transmissibility is output divided by input. So if we multiply the input times transmissibility, we get output, which is the green curve shown here. And so the end output that the unit sees is what's shown in green. At low frequency, we do amplify, as we discussed, the vibration, but at high frequency where there's a concern, we're isolating. Overall, for this example, we're below 5 Gs compared to the 10 G limit for this unit. All right, we'll put our calculators down for a second. We'll talk about load product types that we can provide. There's 4 different categories we're going to talk through here. The first is what we call our catalog solutions. We have an Aerospace catalog which has over 300 different part numbers available to it. Many of them are in stock, available for developmental purposes if you're looking to test something in short notice. 2 unique characteristics about catalog parts is we cannot do unique marking to them, nor can we do unique acceptance testing to them. We have to take parts from a box, put them into a box to ship to you with no modifications. That being said, we have products called dash number solutions. Dash number solutions have one basic concept behind them, which is we're using the existing molds that we use to manufacture our parts to make these parts. However, our molds have lots of flexibility to make modifications that we can do. For example, we can change the elastomer we squirt between the metals, or we can change what metals we use instead of aluminum, stainless steel, whatever it may be that we need for a specific application. The coatings that we apply to the metal can also be modified or finishes. Interfaces in some instances can also be adjusted, making the hole smaller to accommodate a smaller bolt or making it threaded instead of a through hole. Those could be options depending on which isolators we're talking about. And then finally, our dash number solutions can allow us to do unique acceptance testing if applications require it. And of course, because of this, we have a unique part created. We can have custom marking as necessary, deemed by us and our customers. The third category of mounting solutions is what we call our custom solutions, and it's exactly as it sounds. They're ground-up designs, and it's an optimization for all the characteristics that are of interest: our performance, weight, space, and ease of installation. Additionally, we recommend that you engage Lord early on this to ensure we have enough space to fit a mount and can accommodate the interfaces necessary. Additionally, Lord's capable of supporting not just the design, but also the analysis, manufacturing, and test of our isolators. And the fourth category is what we call custom solutions with integrated structure. They are also ground-up designs, the same as custom solutions, and it has all the same benefits as our custom solutions. What we often find is integrating mounts into systems cause these awkward or unique brackets that can sometimes be complex to integrate or align with other suppliers. And what Lord can do is integrate those components with the elastomeric part. It reduces part number and interface complexity, reduces the assembly hardware, and optimizes the overall system performance. Now we're going to shift gears again and talk about some considerations when selecting an isolator. The first couple points here on the left-hand side, I think we all recognize. Understanding the system weight, as we discussed. Understanding the CG location of a unit being mounted, and the mass moments of inertia to understand how it rotates, and the mounting points that are available. However, we also need to consider a lot of other factors that aren't always reviewed in first pass, such as the environmental conditions, what the specific vibratory inputs are, and what the performance of those are expected to be. Any transmissibility requirements, system resonant frequencies, sway space limitation, and fail-safe requirements. On the right-hand side, I'm showing an image of our technical data sheet, or the questionnaire. It's in our catalog. It's intended to be a way to start a discussion with our technical group and understand what characteristics may need to be considered when mounting a system. So the process for selecting an isolator. Step 1, fill out that technical data sheet. Step 2, send it to our Aerospace tech support email address. This is an email address that we always have an engineer on hand reviewing, providing recommendations or technical guidance for our catalog products and materials. Or you can give us a call and then move on to the next task. All right, so I joke about that as well. On the right-hand side is typically the approach that we take when we are reviewing an application for our customer. First, we're assessing the environmental conditions, considering fluid exposures, temperature range. Then we're looking at the dynamic performance. What stiffness do we need and what are our damping limitations? Third is then sizing an isolator to meet the loading requirements. This is both considering dynamic loads and static loads. And then 4 and 5 is looking at the extreme performance. We need to consider how elastomer will respond to the worst case condition, maximum temperatures and all the dynamic conditions. And then finally, the fatigue assessment. We have some proprietary data to estimate the fatigue life of elastomer. And why I point all this out is, though all these steps may not be available for all of our customers to do on their own, this isn't necessarily picking out a bolt. There's a lot of characteristics that need to be considered. All right, we're going to pause here again for a second and prompt another poll question. Who's responsible for selecting an isolator? All right, we're going to go through a quick example here. So on the right-hand side, we have some basic technical data. We have a system that weighs 20 pounds. We're going to assume that there's 4 mounts, but we're looking to isolate 64 hertz. The things that we're going to look at today is finding the maximum mount stiffness to ensure that we isolate 64 hertz. We're going to select an isolator, and then we're going to estimate the system's dynamic deflection. All of this is going to assume a CG-centered system. So step 1, we're going to find the maximum mount dynamic stiffness to ensure we isolate that 64 Hz. On the left-hand side, we recognize our favorite equation to correlate stiffness to natural frequency. So what we're going to do is rearrange this equation and align it so that 64 Hz occurs at that intersection between amplification and isolation. And I have that shown here. That's where that factor of 1.41 comes from. That's the square root of 2 as we previously discussed. We estimate a system dynamic stiffness of 4,200 pounds per inch. We're going to divide that by the number of mounts that's supporting the system to get an estimate for a mount stiffness, 1,050 pounds per inch. Step 2, let's pick out an isolator. I'm arbitrarily going to pick the AM006 series from our catalog. We'll zoom on the AM006 series and we see that the AM006-10 has a dynamic axial spring rate of 932 pounds per inch, which is less than the 10,050 that we're requiring for this system. Now let's rearrange this and estimate our system's natural frequency using those mounts. We're going to go back to our original favorite equation up at the top, plug in our dynamic stiffness for the K prime T, and estimate a natural frequency of 43 Hz. And we'll confirm by multiplying that by a factor of 1.4, the square root of 2, that we in fact are transitioning into isolation at 61 Hz, which is before the 64 Hz that we need to isolate. Now the third step. We're going to determine the deflection of the system. Again, we're assuming this is a CG-centered system. We estimate the maximum transmissibility of our BTR silicone to be 3, which we find from the graphs in our catalog. And our input acceleration is a 2g sine sweep. We can convert that input acceleration to an input deflection using the equation on the left, and we estimate 0.021 inches double amplitude. Then again, recognizing transmissibility as output over input, we can convert that to an output deflection, and we get an output deflection of 0.063 inches double amplitude, or single amplitude 0.032 inches. And that's the estimate we would use for ensuring we have adequate sway space for a mount of this stiffness. Our catalog also provides details and steps you through how to select isolators for different input conditions and analyze the expected response, both for sine inputs that we did here, random inputs, and shock input conditions. We'll switch gears again. We're going to talk about some LORD capabilities. In terms of analysis tools and software, LORD has internally developed single-body and multi-body analysis software. It uses stiffness and damping properties at each mount point and is a non-FEA type system. It assumes rigid body motion and a lump mass. The reason we do this is to reduce turnaround time to analyze models. For dynamic motion, it's typically safe to assume rigid body motion and can get a quicker response in terms of estimating load and deflections of mounts and displacements of system. We have mount-specific software to analyze the elastomeric portion. Those are also internally developed systems and also integrate our elastomeric fatigue predictions. And finally, we also have industry-standard tools such as ANSYS, CATIA, and Inventor for designing and analyzing our mounts. In terms of materials and elastomer, LORD internally formulates and manufactures its own elastomer. We're capable of tight tolerances, performance, which is applicable for some product types. Some of them have inherent variability to them, but others we can really tighten down the screws if we need to. And we have a wide range of elastomer types that are available to us. On the right-hand side is actually a small cross-section of that. We see natural rubbers as well as nitriles, neoprenes, fluorosilicones, and regular silicones. And each of those categories actually have a significant number of options within them. And finally, each flavor of elastomer, the way we think of it, has its own stiffness range associated with it. And then finally, our testing capabilities. LORD has a 14,000 square foot facility within our facility in Erie, Pennsylvania. The purpose is risk reduction testing, qualification testing, as well as developmental testing at the material level. This test lab supports all of our product line, all of our mechanical product lines, including our industrial products, all of our aerospace product lines, engine attach, rotary wing, equipment isolators, as well as the development of elastomeric materials, as I mentioned. Some of the testing capabilities include static testing, dynamic testing, fatigue, testing environmental and thermal testing for DO-160 or Mill 810 type requirements, as well as our favorite vibratory testing with shakers. We have both 3K and 8K shakers and some modal shakers up to 9 kilohertz. All right, another poll question. Who does the dynamic analysis for your mounted systems? I want to briefly take a minute to talk about some application examples that could be applicable for platforms that are converting to electric systems. As we previously discussed, these aren't the limits of applications, but some examples and potential trends that we're either seeing or expect to see. For mounting equipment, we've talked a lot about this already, but to elaborate further, what we expect to see that's different for these platforms is new types of components that we might not see on traditional platforms. Some examples being large batteries, electric converters, and data management hardware. Some things that will stay the same is the goal to isolate high frequencies that cause damage or accelerate degradation of the units being mounted. There's still many types of equipment that we see on traditional aircraft that will still require isolation, like FADECs, ECSs, electronics and guidance system, PDUs, and the list goes on there. Lord's past experience with design for these type of applications, both relative to our knowledge and products, is not any different for these applications. And finally, environmental conditions. The environments we'll expect to see are no different from our past experience in rotary wing platforms, fixed wing platforms, military or commercial. Some things to keep in mind here. For our single degree of freedom systems we've been discussing, they're great to understand the concept of vibration isolation. However, considering actual systems and the rigid tubes and stiff cables or other connections can negatively impact dynamic performance, since they will act like stiff springs with a low loss factor. As we see more rotors on aircraft, sign-on-random type input conditions will become more common, and these can be complex to predict. And finally, elastomeric isolators are not good thermal conductors. As we've all been hearing about, thermal management and dissipation are related to the ever-growing need for increased battery and efficiency capability. Switching gears here to EPUs, or the electric power units that we're replacing traditional combustion engines with. The differences here are typically EPUs are higher torque for a given weight. The reduction in weight causes a higher natural frequency, assuming the mount stiffness doesn't change, and higher torques causes larger deflection. Some things that stay the same, again, the goal to react thrust and torque of the engine while isolating the propeller natural frequencies. Mount configurations and attachment methods, like using focalizations, can still be applied and beneficial for EPUs. Also, assuming the interfaces match standard general aviation applications, or it has a wide array of commercial off-the-shelf parts that are available. Looking forward, Lord is progressing on multiple EPU applications, which of course, like all of us, we're very excited for progress on this to see how things work out. And finally, we expect there to be some customizations for these mounts for EPUs that are specific to them to meet the highest performance needed. And finally, rotor heads. This is a little different. As we mentioned at the beginning, this webinar is not focused on rotor head products. However, as we go through this, I think you'll understand why we're talking about it in a Vibes 101 discussion. What we see here that's different is the number of rotor blades and the rotor size, as well as the method of flight control. What hasn't changed? The options for rotor configuration. At the top is the simplest configuration. It will be the same as an EPU mounted vertically. At the bottom is the most complex, fully articulated and tilt rotor configurations. Lord has a wide variety of products that support motion control of blades. Some examples that are shown on the far right. At the top is a tension torsion strap, or TT strap. Below it is a trunnion bearing. Both of those are used on the lower complexity rotor configurations. And at the bottom is the complex configuration of Lord elastomeric mounts overlaid on a tilt rotor aircraft to show for contrast. And then finally, Lord's experience with rotor dynamics and vibration isolators. And I think you see where I'm going with this. As there's a shift to more rotors, the need for less complex motion of the rotor blades for control authority, the goal of elastomerics may shift from motion accommodation to vibration isolation, and that's why we're talking about it here. Secondly, though it may seem obvious, anything on a rotor head needs appropriate design consideration and time to develop due to the complex motion and criticality of the application. So we do encourage you to engage Lord early to discuss. And we'll continue here to talk about some mounting considerations. I previously mentioned the word CG-centered. The CG-centered system, if we look at the images in the left-hand column, is two examples where we have the isolators, and if we draw lines between all the isolators, it aligns with the CG of the unit. These are two different options on how to accomplish that with mounting locations. In the center is two actual examples of how you can accomplish that. In the top middle, we can see the pedestal shown on the image on the right, sitting sideways on the front corners, and there's two more hiding in the top back corners. In the bottom image, we see a platform surrounding the unit with our HT style mounts in 4 locations around the outside. The benefits of a CG-centered system is input in any direction causes pure translation, no rocking motions. This is a much more even distribution of loading across isolators. It results in smaller deflections compared to a rocking system, and it's more accurate in terms of prediction for a system's response. Now, let's compare that to this slide. On the left-hand side is 2 CAD images with our dynamic modeling software overlaid on it. The colored triax represents mounting points and where all the green lines come together at the CG location. On the right-hand side, we have a transmissibility curve graph. And this doesn't look like the previous transmissibility curves we've seen. And what we see is each of these 3 curves is from the same unit. They are the 3 different transmissibility curves for 3 orthogonal directions. So when we talk about trying to target isolating a specific frequency or trying to have a natural frequency within a certain range, we can see the complexity and challenges when we have non-CG-centered systems. And one final consideration when mounting using isolators is the surrounding structure. On the far left-hand side here is my mock-up, and it's an exaggeration of things we typically see. We can see our AM003 mounts and a very flimsy bracket that attaches them to this box. And when we look at this, what we see is springs in series. And the effect of this is the system will have a lower natural frequency than expected. The transmissibility at resonance will be higher because we're also flexing the metal. It also can induce stiffnesses on the bracket or stress on the bracket that may not be anticipated or desired. So in general, Lord recommends that structure around in the load path of isolators to be 7 to 10 times stiffer. All right, now we're going to go to some specifics related to the design of elastomer and the things that modify the performance. If we go to our favorite equation, we want to talk about what are some factors that affect the stiffness of an isolator. And there's 3 major factors we're going to talk about here. The first is the elastomer shear modulus. That's a material property that we can control. So as we look at our part in the catalog, we see different stiffnesses, and it's the same elastomer but a different shear modulus. Second is temperature, which I think we all recognize the effect. On the left-hand side, we see a graph with temperature in the x-axis, and we have a stiffening ratio in the y-axis relative to room temperature. And if we look at this trend as a whole, it's exactly what we expected. As we head left and decrease temperature, elastomer stiffens. As we head right into higher temperatures, the elastomer softens. And as we see, each elastomer has a unique characteristic associated with it. On the right-hand side is a similar graph, but on the vertical axis, we have the resonant transmissibility. So not only are we affecting the stiffness of the part, but we're affecting the max transmissibility at resonance. And then third is the dynamic input. And this one's most critical of all the things we're going to talk about today. On the x-axis, we have the strain that an isolator is exposed to, and on the y-axis, we have the dynamic modulus, or we can equate that to the stiffness of a part. And the way that we read this is, if we start at a nominal condition, so I'm going to start at 10, then head left, what we see is as we decrease the strain on a part, the part stiffens. So if we take a single part from the catalog, put it on a shaker head, depending on what input condition we expose it to, the stiffness or natural frequency response of a unit could change. And as we increase strain, head to the right on that graph, the elastomer will soften. And that's something that we frequently need to account for. And again, on the right-hand side, we see a similar graph, but in the y-axis, we see resonant transmissibility. And as you guessed, strain also has an impact on that as well. Now, why do we bring this up and say it's so important? We're going to quickly go back to the slide where we picked out our AM006-10. We picked it out because it had a stiffness of 932 pounds per inch. However, what we have to recognize is that stiffness is rated at an input condition of an 0.36-inch input. Our input was less than that. And as we decrease strain, that means the part could in fact be stiffer than the 1,051 pounds per inch that we need for